Hello students, my name is Shashank Shekhar and today is the third lecture of the chapter Amines. So considering yesterday's class, we have seen different things like methods of preparation, okay, and also we have covered the nomenclature and classification. So let us talk today about this physical and chemical properties. So we will be focusing on it this part only today, and we will see the second part of this physical and chemical properties in the next lecture also, because there are many more chemical properties which will be left today that we will cover in the next class. So let us start our today's class. So these are the topics that we will cover, starting from the physical state. So we basically see what is the color of the physical state. By physical state, I mean that whether it is solid or liquid or gas. Okay. So first we will see about the physical state of amines. Then we will move to solubility. Depending upon the nature of the amine, we will decide the solubility both in organic and inorganic solvents. Further, we will move to boiling point and also see a comparison of the boiling point. So, boiling point of different functional groups have been covered previously in the lectures, and we will compare the boiling point of the amine with those. After that, we will move to reactivity of amines, and by nature, amines are basic, and we will see the cause behind its basic nature also. Then further we will talk about amine salt. So amine salt are basically formed from amines only by some reaction that we have seen yesterday. That reaction was between your amine and your, say, halogen, okay, haloalkane. Further, we will do the quantitative treatment of basicity. So as we have seen that we can quantify the basicity or acidity of any organic or inorganic molecule with the help of K and pK or Kb or pKb. So we will do that. Further, we will compare the pKb of different amines, okay, and then we will see the cause of the, say, our basicity. And why are we seeing the cause? We are seeing the cause because so that we can compare it with the other amines. Okay, so we will see the structure basicity relationships of amines. So we are basically defining a relationship between the structure and the basicity. So each of the property, whether any chemical property we talk about, is dependent much more on the structure. So we will look at the structural aspect. Okay. Further, we will move to solvation and basicity. So this is a topic that will be more clear if we study the structure and basicity. At last, we will try to compare aryl amines and ammonia, and also alkyl amines and ammonia. So first, let us begin with the physical state. So if we talk about the lower aliphatic amines, so they are fishy or having fishy order, and they are, say, liquid in nature, in liquid state, and the higher ones are solids. So the reason is very obvious. It is due to the van der Waals force, and you know the van der Waals force is directly proportional to the molecular mass. So since lower amines have a lower molar mass, or you can say molecular mass, so there will be less strength of this van der Waals force, and hence a weak state, I would say, is formed, that is liquid. And as we move to higher states or higher homologous series of the amines, you will see that the molecular mass will increase, and hence the van der Waals force between the molecules will increase, resulting in a formation of solid structure. After that, aniline and other aryl amines. So if you talk about the aniline, so aniline basically is benzene attached with NH2. Okay, so this is called aniline. We have a benzene here and NH2. This is called as aniline. So if you talk about the aniline and other aryl amines, so they are colorless, but get colored on storage due to atmospheric oxidation. So what does it mean? So it is being said here that if they are kept in isolation, then they are colorless, means they have no color. But if we expose that aniline or aryl amine to your atmospheric oxygen, then it would go atmospheric oxidation, that is the addition of oxygen, and it gets colored, means the compound that will be formed upon oxidation is colored in nature. Clear? Now this was one of the physical property, that is about the physical state, in which we talked about the mainly about the order, the physical appearance, where they talk about color, and liquid as state and solid state. Now we will move to solubility. So if you talk about the solubility, so the lower aliphatic amines are soluble in water because of the hydrogen bonding. But as we increase the length of the alkyl chains that are being attached to the nitrogen, then the solubility decreases, and the reason is obvious. It because the hydrogen bonding becomes less efficient. So due to this reason, the higher amines are generally insoluble in water. So if you look at the structure of amine, so suppose we are taking a primary amine, say, so it will have two hydrogen and one R. Now, as we dissolve it in water, this hydrogen will get attached due to hydrogen bonding, extensive hydrogen bonding. It will be attached to the water molecule. So there will be an interaction. Similarly, the other hydrogen will also have interaction, and this is the interaction between oxygen and hydrogen. Similarly, the water molecule has also H in it, that is the hydrogen in it. It will interact with this nitrogen. Now, what will happen if we take, say, any higher alkane, higher amine, by which I mean that we are increasing the chain length in this way. RCH3, suppose now we put it as C2H5, this will be a higher chain. Okay, then we will have C3, C3 to just 617, 3C3H7. So as we substitute R with CH3, then with C2H5, then with C3H7, as we keep on increasing the number of carbon atom, this will decrease the solubility of the amine in water. Okay, clear? Now, one more thing. So, what will be the solubility if we compare with the help of, say, classification basis? Say we are taking the primary amine or we are taking secondary or tertiary. So, what will be the result of it? So, if we take the tertiary amine, say we are taking a tertiary amine, suppose we have a R here. Okay, here also H will be substituted with R. This is the example of tertiary amine. First of all, the number of extensive hydrogen bonding has been reduced. Initially, three water molecules were being attached to this molecule through hydrogen bonding. Now, since two hydrogens have been removed, this hydrogen bonding is now being reduced to one of them. So only one atom is now being capable of doing the extensive hydrogen bonding. Also, this R is now depolarizing. I would say it is depolarizing the bond that is being present here, and hence it is kind of decreasing the negative charge on nitrogen, due to which its hydrogen bonding extent is also decreased. Now, if we compare, say we compare this solubility of amines, say we take a primary amine and we take alcohol. R group is taken such that the molecular mass is comparable. Okay, enough on this page. So if we compare the solubility, then you will see that the solubility of ROH is higher. Okay, the solubility of ROH is higher, and the reason is quite simple. Because of the higher electronegativity of this oxygen atom, the polarity of the bond is increased as in comparison with this amine, and due to this reason, the hydrogen bonding that was expected to be much more stronger in case of amine is now reduced due to this smaller electronegativity, and is greater in the case of alcohol. Now, due to this reason, the alcohol is having say greater solubility. Now, amines are soluble in organic solvent like alcohol. So this is also a good point to remember, that amines are soluble in organic solvent and ethers and benzene. So although there is a dipole moment in ROH and say RNH2 or any other organic molecule, but still they are organic molecule. The dipole moment will never be in par with this inorganic molecule like HCl and HF, and hence its solubility will be always favorable in organic solvents. So we can have many organic solvents like ether, benzene, alcohol, DMSO, and many more. So this is about the solubility. The next physical property we will talk about is boiling point. Now again, this boiling point is well defined with the help of hydrogen bonding. So this alcohol, so alcohols are much more polar than this amines, So it is very clear from the structure only. If you look at the structure of, say, alcohol, it's just ROH. But if we talk about amines, it is not that much polar. First, due to less electronegativity of this nitrogen atom, and second, the orientation of the bond. So it has two hydrogen. So this electron density is being distributed over these two bonds. In addition to the, say, this kind of bonding that is present in alcohol, it has one more. It has one more hydrogen attached to it. Now, due to this reason, the polarity is also decreased, and hence the hydrogen bonding. Hydrogen bonding is also decreased. Due to this reason, the alcohol are having a higher boiling point in comparison to the amines. Now, if I talk about the amines itself, if I compare the boiling point of amine itself, then the primary and secondary amines are engaged in intermolecular association due to hydrogen bonding. So it is very clear that for hydrogen bonding, there should be a pair. I would not say pair. There should be a proton that should be attached to a say electronegative element like nitrogen, chlorine, oxygen, fluorine, or any other. Okay, but if we take the example of tertiary amine, we do not have any such hydrogen that can be available for the hydrogen bonding. But primary and secondary alcohol have those things. Now, if we compare the primary and secondary alcohol, so as we have talked earlier, that this hydrogen bonding is having greater extent in case of primary amine, in comparison to your secondary amine, and also the number of interaction is more. So, due to greater say hydrogen bonding, greater extent of hydrogen bonding in case of primary amine, the primary amine have a higher boiling point. So we can see the trend that the primary is having the highest boiling point, then comes the secondary, then comes the tertiary. And for tertiary, the reason is that we do not have any intermolecular association. By association means hydrogen bonding. Okay, so we are done with the physical properties. We will just look at a comparison at last to say the outcome of all the discussion that we have. So let us compare the boiling points of some amines, alcohols, and alkanes. So different functional group are here, and we will compare them. First of all, let us talk about amine. So if we see, there are three amines here. Primary, secondary, and tertiary all have a molar mass of 73. So we have kept the molar mass constant so that your van der Waals forces do not vary much. Now, if I look at the boiling point, you will see the primary amine has a greater boiling point. The reason is very obvious. It is due to say greater hydrogen bonding, greater extent of hydrogen bonding. Now, if we look at the normal alkane here that is being present here, you will see that the normal alkane have a smaller boiling point. What is the reason behind it? The reason behind it is that there is no hydrogen bonding or no polar induced interaction, due to which it has a lower boiling point. Now, if we compare the boiling point of say amine with alcohol that is being present here, so this is alcohol, its boiling point is higher. Okay, so its boiling point is higher in comparison to amine, and the reason is very obvious, due to greater polarity of the alcohol. So we have a boiling point of 390. Now, if I try to write the order here, then I would write that first of all, the alcohol has the highest boiling point, then comes 1 degree amine, then comes 2 degree amines, and 3 degree, and at last we have the normal alkane. Okay, clear? So I think you should try to be more say approative in case of this say comparison of the boiling point. Okay, clear? Now next, let us see the reactivity of amines. So if I talk about the reactivity of amine, so for that again we have to go back to the structure of amine. So amines have a nitrogen and hydrogen bond, okay, and the electronegativity of nitrogen is much more than the hydrogen, and the presence of the lone pair, that is being on nitrogen, it has a greater, say, electron donating tendency, or you can say it has a high basicity due to that. Now the number of hydrogen atom attached to the nitrogen atom also decide the course of reaction of amines. That is why primary, secondary, tertiary, and primary, secondary, and tertiary amines have the difference in reactivity. So this is very obvious. So it will have a difference in our reactivities because as we increase the chain, say as we increase the number of alkane on nitrogen, this will of course disturb the polarity of the NH bond, and also the tightness with which the lone pair is held by the nitrogen is also being obstructed by the inclusion of this R group. Okay. At last, I would now make a statement that since nitrogen has a lone pair on it, so it can donate electrons. Now, since it can donate electrons, it can act as a nucleophile. Okay, it can act as a nucleophile. What are nucleophiles? So the definition is clear from the name only. Nucleo means nucleus, and phile means loving. So nucleus loving. And what is the charge that is present on nucleus? Positive charge. So it is basically positive loving. And why is it so? Because the lone pair is of course the electrons, and electrons are negatively charged. Now let us look at the basic character of amine. So why is this amines basic? We will say, and why is this amine basic? We will devote some of the upcoming slide to this thing only to understand why are the amine basic and what is the extent of basicity. We will look at the various aspects, whether we talk about structural aspect or talk about the lone pair, say lone pair extraction or some, all of these. We will look at all of these. Okay. So first of all, let us see a reaction that is being present here to define the basicity. So what we have done, we have taken an amine and we have reacted it with a protonated acid. Okay, so I would say it is a Arrhenius acid. Okay, clear? Now what will happen? This lone pair will take up this hydrogen and will result in the formation of a salt. So it is a salt. Why is it a salt? First of all, because it has a negative addendum, and sorry, it has a positive addendum and it has a negative addendum, and it is formed upon the reaction of a base and acid. So it is a salt. Or we can do the same reaction with the help of aniline also. So we are taking an aromatic amine, so it will also give a aniline, say it will also give a salt, and here we have taken HCl, and the salt that is being formed is called as aniline chloride. So we can say that amines react with acid and act as a base. Acting as a base, it reacts with acid to form salt. Now we will talk about this amine salts. You must have seen these amine salts in case of the reaction, or you can say preparation of the amines, in which what we have done, we have prepared a salt and then we have reacted it with NaOH at the last to give our amine. The same reaction is being written here also. So what we have done, we have taken a salt and we have treated with the base to get the amine. Now, in contrast to this amines, these salts are soluble in water. The reason is very obvious, because it completely dissociates in water, and the negative part goes to the hydrogen bonding, and also the positive part goes to the hydrogen bonding, and dipole interactions are also available there for the solvation of this salt. But on the contrary, it is not soluble in the organic solvents, because organic solvents are not polar in nature. And you know the very famous statement that like dissolved in like, and since it is a polar one, so it will not be dissolved in this salt will not be dissolved in this, because it is a non-polar solvent. Now this reaction is the basis for separation of amines from non-basic organic compound insoluble in water. So what do? We treat the amine with, say, OH. okay, sorry, HX, and then we separate it on the basis of the solubility, because it is soluble in say inorganic solvent, or you can say polar solvent. So if we convert this amine into salt, then we can dissolve it in water, which is polar in nature, and further we can crystallize it to get our salt back, which can be converted back to the amine with the help of a base. Now the reaction of amine with mineral acid to form ammonium salt shows that they are basic in nature. Now they are kind of Lewis base. Okay, they are Lewis base. Why? Because Lewis base are those which can donate electrons, and nitrogen is donating electron in this case, so it is a Lewis base. So this was about the amine salt. Now let us do a quantitative treatment. How does the basicity goes? We will do a quantitative treatment of that. So let us start with our equation. What is the equation that we have taken? We have taken the hydrolysis of this amine. So if we take an amine, it will act as a base and treat it with water, which will act as an acid. Then it will give RNH3 plus, because the H2O has donated its proton to the amine, and amine is being converted to RNH3 plus. And since one H has been taken by the H2O, one H has been removed from the H2O, we will get OH minus. Now, if you try to write the equilibrium constant K for it, then how it will be written? The reactant concentration will be in the denominator, and the product concentration will be in the numerator. So first of all, the product concentration on the upside. So we have taken the concentration of RNH3 plus and multiplied it with the concentration of OH minus. Then we will divide it with the concentration of your reactant, that will be our amine and water. Now, during hydrolysis, we have seen this thing earlier also, we take a excess of this water. Now we multiply the concentration of water with the equilibrium constant, and it will be still constant. Why? Because the concentration of water is not changing much throughout the reaction. Therefore, it will give a value that will be equals to Kb, called as Kb. So we have seen K earlier for case of the carboxylic acid. Similarly, we can have Kb. Now, we can also take the negative logarithm of the K, like we have taken for K, we can take Kb. Negative logarithm of Kb, we can get pKb. Now again, if you don't remember why the pKb is taken in and not Kb, because Kb contain values like 10 to the power minus 14, 10 to the minus 13, and that are difficult to remember. But pKb will be simple numerical values like 14, 13, 12.5 or 13.7, and it would be easy to handle also. So due to this reason, we take or consider pKb values rather than Kb values. Now let us compare Kb values of some amines. So larger value of pKb is smaller the value of pKb. So it is clear from previous lecture only, where we have seen K and log pK, I would say. Here also pKb is higher than pKb, Kb, if Kb is higher than pKb is smaller, and vice versa. Now the pKb for amine is 4.75. Okay, it is 4.75. Now if I compare the pKb of ammonia with methenamine or ethenamine or any other amines, then you will see that methenamine or ethenamine have a greater smaller pKb, means they are more basic than our normal ammonia. So aliphatic amines are stronger bases than ammonia due to plus I effect. So since we have alkyl chain on nitrogen, they will donate electrons on nitrogen and hence increase the basicity of the our amines. Now we can see this with the help of our table, where we can see that the pKb of ammonia as mentioned is 4.75, but it is greater than any amine that has been mentioned here in this table. We have various values starting from 3.38 to 8.92. Okay, 3.38 to 4.22. So here we have taken up till this part, or we take this also. I will not consider aromatic system now, because there are different thing to handle. So this is aromatic system. These are all aromatic system. Okay. Now all of the remaining compounds that we see have a lesser pKb value than the ammonia, and hence they are highly basic in comparison to ammonia. But if we compare it with the aryl amine or any aromatic system, you will see a change in that trend. And the reason we will see in the last slide of this class today. But this is the table. You should be aware about this. Now, if I talk about the aromatic amine, why is it less basic? We will talk that in the next upcoming slides. Now, let us try to build a bridge between the structure and basicity of amine. Why is the structure? How is the structure affecting the basicity? So, basicity of amine is related to the structure. Okay. Now, the basic character of amine depend upon the ease of formation of the cation by accepting a proton from the acid. So, how easily the amine can accept electron, that will decide the basicity of our amines. The more stable the cation, so after say reaction, the cation will be formed. So if the cation is more stable, that is formed, then the basicity will be higher, and if it is less stable, then the basicity will be lower. Now first let us try to compare alkane amines with ammonia. Okay, so we have taken the reaction here. So we have done the reaction of our alkane amine with H plus and we got this cation. Okay, now we have taken ammonia and treated it with H plus and we got this species. Now if I compare the stability of both these cation, you will see that this species is more stable because the nitrogen positive charge is being stabilized by plus I effect, that is being facilitated by the R group that is present in the case of amine. While in case of ammonia, we do not have any such group and hence it is less basic than the alkyl amines. Okay, so we can say that the alkyl amines are stronger bases than ammonia. So this was the structure basicity relationship of amines. Now let us look at a very interesting topic here. So students get confused that why is the basicity differed in case of aqueous phase for amine. See, I cannot justify the order very much clearly because it is very difficult to consider all the aspects of the say solvation aspect or all those. But still, I would try to build a proper connection. Okay, but still you have to remember the order. First of all, let us take the simple task of explaining the gaseous state. Now, if I talk about the gaseous state, the reasons are obvious, that since the number of R is increasing as we move from primary to secondary to tertiary, therefore the basicity of the nitrogen is being increased. Okay, so it will follow this trend in case of gaseous phase only, because the positive charge that will be coming on nitrogen after accepting the hydrogen will be stabilized by 3 different R groups, while in secondary we have only 2 and in primary we have only 1. So in gaseous phase, and I am repeating it again, that only in gaseous phase this trend is seen, that tertiary amine is the most basic one, then we have the secondary amine, then we have the primary amine, at last we have the ammonia. But what happens if we take aqueous state? So all the game that we have seen now changes, and the reason is that the water comes into play, the solvation comes into play, steric hindrance just try to deframe the basicity, and all of this factor including say solvation or we say steric or the nitrogen lone pair availability results in a very say random trend, and that can only be remembered and cannot be explained wholly. Okay, so in aqueous phase, the substituted ammonia cation gets stabilized not only by the electron releasing effect of the group but also by the solvation with water molecules. So what does it mean? That if we talk about the gaseous phase, then we have only nitrogen that is being say facilitated, or you can say it is being supported by the alkyl groups on formation of positive charge on it. But in case of say water aqueous phase, we have water molecules also. Okay, and those water molecules also stabilize the positive charge. And how does it do so? By the help of hydrogen bonding again. So if we take a primary amine, then it will have greater extensive hydrogen bonding as compared to the secondary, and then we have the tertiary. So we can say that the greater the size, so we can say the solvation is say higher in case of 1 degree, then we have 2 degree, but in case of 3 degree. But still, the order will not look like the one we expected. Because we also the role of R, we have also the role of solvation. So how will you decide? So for that, we have to just remember the order. There is no other option because all of this is a combined effect, and combined effect cannot be explained wholly. So the order of stability of iron first of all looks like this. So we have mentioned the reason behind it, but the order of acidity we will see it later. For case of amines and ethyl, we will see it later. Clear? Okay. Now next, what about the basicity? So if we take simple CH3 group, then we have a different basicity. If we have a C2H5 group, we have a different basicity. Now again, a different thing to tackle. Here comes the role of the steric. Okay, steric comes into play because C2H5 is having greater steric hindrance because it has an extra carbon on it. Now we have three factors: solvation, steric effect, inductive effect. Okay, so all of these three factors now try to produce a third result that is absurd and not according to our primitive ways. Okay, so we cannot just say that this is the reason and this is the order. We cannot do so now because we have three factors that are now contributing to the basicity of this amine. So we see a very random order here. So if we take the case of methyl substituent, we will see that first of all the 2 degree will stable, then we have the 3 degree, then we have 1 degree. But what is the case for say ethyl? So this is the case for ethyl. Sorry, this is the case for ethyl. If we take ethyl in, that will be attached to the nitrogen. But what is the case of methyl? So methyl will have 2 degree, but it will then have 1 degree. At last it have 2 degree, but still NH3 is on the last. Okay, we can take any medium, but still the NH3 will be on the last. So this is the overall order. Sorry for this, it will be 3 degree. Okay. So what is the total outcome of this? That we have three factors that are deciding the basicity of the amines in water. The first one, inductive effect, that is coming from the substituent that is being directly attached to the nitrogen. Second, we have solvation effect. So the hydrogen bonding is now deciding the solution effect. And third is the steric hindrance. So steric hindrance basically that is the hindrance that is coming from the alkyl chain that is being attached to the nitrogen. Now all of these do a subtle interplay and create a different order. So if we talk about the aqueous phase and we talk about the ethyl, then order of basicity is 2 degree, 3 degree and 1 degree. But if you replace the ethyl with a methyl, then the order changes and it is 2 degree, 1 degree and then 3 degree. Means 3 and 1 are interchanged. So we can say that for aqueous medium, methyl will have the order. If the substituted hydrogen is replaced by methyl, then the order goes like this: 2 degree, 1 degree and 3 degree. But if we have ethyl in place of methyl, then the order goes like 2 degree, 3 degree and 1 degree. So this 213 and 231, this you should remember. In case of methyl it is 213, in case of ethyl it is 231. And this is only and only for aqueous phase. So if you are dissolving NH2 in water, then and then only these basicity rules will be applied. Otherwise, it will not be applied in case of gaseous phase. Clear? Now, let us try to compare aryl amine and ammonia. The value of pKb, we have seen earlier that the value of pKb for aryl amine are higher, very high I would say, in comparison with our regular amines. And what is the reason behind it? So just try to first you try to think about it, then I will explain it. Okay, you can take your time. Okay, so for those who have imagined the system, well and good. For those who have not imagined it, also good. Now let us try to explain it. So we have an aniline here. This is our aniline. Now this aniline has nitrogen on it, and a nitrogen has lone pair on it, which will be donated, and which is the basic reason for the basicity or Lewis basicity of this nitrogen group. But since this is a benzene ring, this lone pair that is present on nitrogen is now being delocalized. So it is a electron donating group. NH2 is an electron donating group. So it will delocalize the electrons and will create this resonance structures. Okay. So due to this reason, we can say that the aniline lone pair are not present on one place. Okay. And hence it has a greater, it has a less chance of donating its electron to the hydrogen in comparison to other alkyl chain. Now, but if we talk about the anilinium ion that is being obtained by the accepting of this proton, then it is stable. Okay, it has only two structures, this one and this one. Okay. Now, what will happen if we introduce substituent in this aniline? What will happen? So if we do this, there will be a change in the basicity. It can decrease or it can increase. It will totally depend upon the nature of our substituent that we are introducing. So from our previous experience or knowledge, I would say that the electron donating group will increase the basicity, because if we have an electron donating group, then it will donate its electron to the NH2. Suppose we have NH2 here, and say we have OMe here. Now, since it will donate electron, this will increase the electron density. Here it will go, and here. This will increase the electron density on the carbon that is being attached to nitrogen, and hence more electron density will be moved towards nitrogen, and it will be easily available for the donation. But what happens if we take electron withdrawing group? Suppose we are taking NO2 minus, NO2 I would say. Now we have electron donating withdrawing group and NH2 attached to it. So this will attract electron towards it. Okay. Now due to this reason, the lone pair is now being attracted to the NO2 group that is being present here, and hence we can say that the basicity of the aniline is being decreased by the introduction of electron withdrawing group. So electron donating group increase the basicity, and electron withdrawing group decrease the basicity. Okay, clear? So this was about the comparison of aryl amines versus ammonia. Now I would ask you some of the examples, and I would ask you to try to compare the basicity of those. Okay, so let us do it. Suppose we have an ammonia which looks like this. Okay, we have ammonia which looks like this. And we have hydrogen here, H. Okay, no problem. Now suppose we have one more ammonia. Ammonia, not amine. And I ask you that which of these, out of these two, which of the one is more say electron donating? Okay, out of these two at nitrogen 1 and 2, which will donate electron? Which one will be donating electron? Okay, I will not now look at this one. Let us first talk about this structure. It has 2 nitrogen. Now if I ask you that which nitrogen will donate electron, then most of the students will say that, sir, this is sp2 hybridized or nitrogen. It is electronegative in comparison to the NH2. Therefore, it will have a less tendency to donate electrons, and hence it will be having a greater chance of donating electrons, and hence it will have a greater basicity. But see, students, the reason is not that much simple, and the example is not that much simple. So if you consider a resonance effect here, we can see that the electron density is being moved from here to here. So instead of these being the most basic, this becomes the most basic because the resulting structure would look like this. It will have a negative charge on nitrogen here, here, and this will be the structure. Now, due to this structure, this nitrogen that is being present here, this one is the more basic one. Now, you can be asked in the exam, you can be given various nitrogen from the same compound and ask that which one is more basic. So remember this, if you look at this kind of structure, this will be the most basic one. Okay. Okay. Now let us take a heterocyclic system again. First, I will take pyrrole and pyridine. Now let me ask you which one is the most basic, this or this. So you would say that okay, both of this are having lone pair, but we cannot decide it, okay, because we do not have any idea about the aromaticity. So those who have, well and good. Those who don't have, let me explain it to you. So if you think that this lone pair of nitrogen can be going into the aromatic system for delocalization, then you're totally wrong. Okay, you're totally wrong, because it is already a stable aromatic system having 4n plus 2 pi electrons. But if you take the extra electron from this nitrogen, that would result in a absurd structure. Okay, that would result in an absurd structure. First of all, that is not possible also. Why is it not possible? If you donate the electrons like this will create a very absurd structure. But if you talk about this has no such compulsions, because the nitrogen lone pair will also go into conjugation. Why it will go into conjugation? It will go into conjugation because this is not aromatic system without the inclusion of this lone pairs. Okay. So I would say, so if you just try to draw the orbital diagram, I'm just drawing the p orbital. Okay. So this will be for the nitrogen. So the nitrogen p orbital, which is not hybridized, okay, the pure p orbital, which is containing the electrons, will be parallel to the pi orbital that are involved in the pi bonding. So this will be involved in the pi bonding. Now this lone pair can be donated here. Okay. And as this lone pair is donated here, this will create a 4n plus 2 pi electron system. You cannot make the system aromatic without the inclusion of the nitrogen lone pair. Okay, clear? Now, due to this reason, since the lone pair is delocalized and not simple delocalization, but the delocalization in aromatic system, a part of the Huckel's electron, therefore its basicity will be very low as compared to the pyridine that is being showed here. Okay. At first sight, the student would say that this nitrogen is sp2 hybridized, or you would say that it is benzene, this lone pair must be going into conjugation. So all those reasons are not valid at all. The reason is that the nitrogen lone pair that is being present in case of pyrrole is not involved in the is involved in the aromatic system to make it aromatic, because it should have 4n plus 2 pi electrons. But in case of pyridine, the reason is not means the case is not so, because it will disturb the aromaticity rather than stabilizing it. Okay, so its lone pair are clearly available for donation. Clear? Is this point clear? Now let us take one more example to look at the basicity. Suppose We take this. And we take this. Now I would ask you, which is the most basic one? Again, do not get confused that this lone pair is going into delocalization in the say system. It is completely localized on this nitrogen. It is on the nitrogen, but it is a sp2 nitrogen. It is a sp3 nitrogen. So this one will be easily, and it will be also comfortable in donating its electron. So it will be the most basic. Okay. So this was about the basicity. We have seen many examples. You will see many more examples when we will talk about biomolecules. You will see various amino acids there. Okay, basic amino acids which has more than one nitrogen, two histidine, and all of those. There also you will need this concept to compare the basicity. So what we have done in today's class. So we have started from the physical properties, and we have seen that the lower alkanes, the lower amines are liquid in nature, and as we move to the higher alkane, they become solid because of the presence of van der Waals force. And the lower alkane have a fishy order. If we talk about the aryl or the alkyl amine, the case is not so. Okay. Then we move to the solubility. So again, the solubility increases as we decrease the molecular size, and vice versa. So as we increase the molecular size, the solubility decreases. So the higher chains of the amines are not soluble in water due to the destruction of polarity. And what is the reason behind the solubility? It is hydrogen bonding. But since alcohol is having a greater polarity of bond, so it will have a greater hydrogen bonding. So it will be more soluble in compared to the amine. But all these organic compounds are organic in nature, and they are non-polar, so they will be dissolved in non-polar solvent. Then we have seen the boiling point. In the boiling point, we have seen that the primary amine are having higher boiling point, then we have the secondary, then we have the tertiary. The alcohol is at the foremost, it's at the first because it has a greater extent of hydrogen bonding. And the ammonia is at the last. Then we have seen basicity, and we have seen that ammonia are less basic than the alkyl amine. And also the alkyl amine are more basic than the aryl amine or the aniline also. The reason is that because the lone pair of nitrogen is being delocalized over the system. Due to this reason, it is less basic. At last, we have seen some examples, and I would suggest you that you go through the example one more time, because this will help you in deciding the basicity, because questions are very often asked from here. Now I'm asking you one more question. So this is a very interesting question. Suppose we have an amine here. So two methyl substituents are present. So it is a N and dimethyl aniline. Now we suppose we introduce a nitro group. So ortho nitro N and dimethyl aniline. Now if I ask you to compare the basicity of this with this, then what would be your answer? What will be the answer? So first of all, remember the first concept, that as the electron withdrawing group is present on the ortho and para position, they will donate electron from this center or this center through minus M effect. Now the steric reason comes into play here. This nitro group that is present here is facing steric hindrance from this methyl group. So if I just try to expand the structure, okay, clear? Now there will be steric clash between these two groups. Due to the steric clash, what will happen? The nitro group will go out of the plane. Okay, the nitro group will go out of the plane, and as it will go out of the plane, so the condition for conjugation is now destroyed, because for better conjugation, the pi orbital on the nitrogen should be parallel with the pi orbital of the carbon, that is of the aromatic system. So I would say that suppose, so let me draw it in a different page. Okay, we have this system. Sorry for this. So this is our benzene system. Okay. So I have only drawn the pi orbital. Suppose we have a nitro group here. It has a okay. Now what we have done, we have introduced a methyl group. Due to this reason, it will just bend like this. Okay. So if something is colliding, it will just bend and go out of the plane. So this initially this nitrogen say orbital was parallel with this carbon orbital, but as there is a steric clash between both of this will just go out of the plane. Okay. And as it will go out of the plane, the chance of conjugation, so there was the initial conjugation, this pi electron were being donated here, so that conjugation goes off, and now the nitro group is not that much efficient. Okay, the nitro group is not that much efficient in taking up the electron. So although this nitro group is present very close to the NME group, that it is not affecting the basicity to that extent, because the nitro group is now out of the plane due to the steric reason from the Me. And for conjugation, the planarity should be the first, you can say this is the first requirement. So due to this reason, the basicity of your ortho nitro N and dimethyl toluene is less. Okay, is high, because the nitro group is now no more attracting the electrons, or is no more taking the electrons of the nitrogen. Okay, so this is a very important example. Now this is also termed as SIP. What is this SIP? It is called as steric hindrance, steric inductive protonation. Okay, I'm not sure about the name. Okay, so let us not focus about on the name, because it's a tool just to remember it, but remember the concept. Okay, so this is a very interesting concept to remember, that why the basicity of this thing is higher than this one. We can have one more example. What will happen if we take this one in place of NO2? Now there will be hydrogen bonding between these. Clear hydrogen bonding. Okay. Now if we compare the physical property, that is the boiling point, so we have seen this also. Suppose we have these two. Now this will also have hydrogen bonding, but with other molecule. This is called intramolecular. Means within the molecule. This is called intermolecular. INTER. This is INTRA. Molecular. Now intermolecular hydrogen bonding is stronger than the intramolecular. Now due to this reason, what happens? The boiling point means since the bonding is strong, so the boiling point of this thing is greater to this. So the boiling point of para nitro aniline is greater than the ortho nitro aniline. So these two results are very interesting. Okay, clear? So this was for today's class. In the next class, we will see some more of the reactions of this, about the reactions of aniline and amine, alkyl amine. For today, this is the lecture. Okay, thank you.